Close your eyes and imagine standing on the shore of an ocean. Feel the gentle rhythm of waves lapping at your feet. Hear the soft whisper of water meeting sand. Sense the vast expanse of liquid stretching to the horizon. Now imagine that ocean extending not just to the horizon, but across an entire world, a planet wrapped in water, where oceans cover every surface, where liquid flows in depths far greater than any sea on Earth. Tonight, we embark on a peaceful journey through the cosmos, exploring the most liquid worlds in the universe, planets and moons, where water flows in abundance, where hidden oceans lurk beneath icy shells, where exotic liquids create seas unlike anything on our home planet. These are worlds where the story of liquid plays out on scales both intimate and grand, where the presence of flowing substances hints at possibilities we're only beginning to understand. Water is precious on Earth, covering about 71% of our planet's surface. Our oceans contain roughly 1.3 billion cubic kilometers of water, an almost incomprehensible volume. Yet there are worlds in our solar system and beyond where Earth's oceans would seem like mere puddles by comparison. There are moons harboring more water than all of Earth's seas combined, locked away beneath frozen crusts. There are exoplanets that may be entirely ocean, with no land breaking their global seas. There are even worlds with seas of liquid methane flowing at temperatures where water would freeze solid as stone. As we drift through this narrative, let yourself float on these cosmic oceans, imagining depths of liquid measured in hundreds of kilometers, surfaces where ice and water dance in eternal cycles, alien seas reflecting the light of distant suns. Feel the gentle pull of these watery worlds, the calm rhythm of tides raised by massive planets, the peaceful flow of substances through alien landscapes. The search for liquid water beyond Earth has become one of the central quests in planetary science and astrobiology. Where liquid water exists, we imagine the possibility of life. Where oceans flow, we wonder if anything swims in those dark depths. These liquid worlds represent not just scientific curiosities, but potential harbors for life, places where the chemistry of biology might unfold in ways both familiar and strange. So, settle in, take a deep breath, and prepare to explore the wettest, most liquid worlds we've discovered in the universe. Let the story of cosmic oceans carry you into peaceful contemplation of these remarkable places where liquid flows in abundance. Before we journey to specific watery worlds, let us first understand what makes a planet or moon liquid, and why the presence of liquids, particularly water, is so significant in our exploration of the cosmos. A liquid is matter, in a state where it flows freely but maintains a relatively constant volume. Unlike gases, which expand to fill any container, and unlike solids, which hold a fixed shape, liquids adapt to their container while maintaining their density. Water is the most familiar liquid to us, but many substances can exist in liquid form under the right conditions of temperature and pressure. On Earth, water exists as a liquid because our planet occupies what scientists call the habitable zone around the Sun, the region where temperatures allow water to remain liquid on a planet's surface. Too close to the Sun, and water boils away into vapor. Too far, and it freezes solid. Earth sits in that cosmic sweet spot at just the right distance for oceans to exist. But this simple picture becomes more complex when we consider other factors. Pressure matters enormously. Deep in Earth's oceans, the weight of overlying water creates tremendous pressure that affects water's properties. On other worlds, thick atmospheres or deep ice shells can create pressure conditions that allow liquid water to exist even at temperatures that would normally freeze it. Internal heat also plays a crucial role. Many moons in the outer solar system are warmed not by sunlight, which is weak at their great distance from the sun, but by tidal heating. As these moons orbit their parent planets, gravitational forces flex and squeeze them, generating friction and heat in their interiors. This internal warmth can maintain liquid oceans beneath icy crusts, even in the frigid outer reaches of the solar system. The composition of liquids varies widely across different worlds. On Earth, our oceans are primarily water with dissolved salts and minerals, but other worlds host different liquids. Titan, Saturn's largest moon, has seas of liquid methane and ethane hydrocarbons that remain liquid at temperatures where water is frozen harder than rock. Some theorists speculate about exotic ocean compositions on distant exoplanets, water mixed with ammonia acting as antifreeze, or even stranger chemical soups under extreme conditions. The depth of liquid layers varies enormously across different worlds. Earth's oceans average about 3.7 kilometers deep, with the deepest point, the Challenger Deep in the Mariana Trench, reaching about 11 kilometers below the surface. But some worlds may have global oceans hundreds of kilometers deep, with volumes of water far exceeding Earth's, despite being smaller worlds overall. Why does all this liquid matter? From a scientific perspective, liquids are dynamic environments where chemistry can happen efficiently. Substances dissolve, mix, react, and transport in ways impossible in solids and inefficient in gases. Life as we know it depends on liquid water as a solvent, a medium for chemical reactions, and a stable environment for biological processes. The presence of liquid water, in particular, raises the possibility of life. Every form of life on Earth requires water. We find living organisms in every aquatic environment on our planet, from freezing Antarctic waters to boiling hot springs, from acidic volcanic lakes to the deepest ocean trenches. This suggests that wherever liquid water exists in stable conditions for extended periods, life might potentially arise. Moreover, liquid environments preserve geological and chemical records differently than solid or gaseous environments. Oceans can sequester gases from atmospheres, dissolve minerals from rocks, and create distinct chemical signatures. By studying these liquids, or evidence of past liquids, scientists can learn about a world's history, its geological activity, and its potential to harbor life. As we explore different liquid worlds in this journey, we'll encounter various types of liquid environments: surface oceans exposed to space or atmosphere, subsurface oceans hidden beneath ice, seas of exotic chemicals, and perhaps even oceans on distant planets circling other stars. Each represents a different expression of how liquids can exist in the diverse conditions found throughout the universe. To appreciate the liquid worlds beyond our planet, we must first understand our own ocean world. Earth serves as our template, our baseline for understanding what an ocean planet looks like and how its liquid systems operate. Earth's oceans cover approximately 361 million square kilometers, about 71% of the planet's surface. These vast bodies of water contain roughly 1.335 billion cubic kilometers of liquid, 1 sextillion, 335 quintillion liters of water. To put this in perspective, if you could somehow drain all of Earth's oceans into a single cube, each side of that cube would be about 1,100 kilometers long. Our oceans aren't uniformly distributed. The Pacific Ocean alone contains more water than all other oceans combined. The average depth of Earth's oceans is about 3,688 meters, but depths vary dramatically. Vast abyssal plains stretch for thousands of kilometers at depths around 4,000 to 6,000 meters. Oceanic trenches plunge even deeper, with the Mariana Trench reaching approximately 10,984 meters at its deepest point, deep enough that if you could place Mount Everest in this trench, more than a mile of water would cover its peak. The composition of Earth's seawater is remarkably consistent worldwide. About 96.5% is pure water, H2, with the remaining 3.5% consisting of dissolved salts, primarily sodium chloride, table salt, but also magnesium, calcium, and potassium salts. This salinity averages about 35 parts per thousand, though it varies slightly between different ocean regions. Earth's oceans exist in constant motion. Surface currents driven by wind and the planet's rotation circulate water around the globe in vast gyres. Deeper currents, driven by differences in water temperature and salinity, create what oceanographers call the global conveyor belt, a slow circulation pattern that takes about 1,000 years to complete a full cycle. These currents distribute heat from the equator toward the poles, moderating Earth's climate. Tides, the rhythmic rising and falling of sea level, result from gravitational interactions between Earth, Moon, and Sunday. The Moon's gravity pulls on Earth's oceans, creating two bulges, one on the side facing the Moon and one on the opposite side. As Earth rotates beneath these bulges, coastal regions experience high and low tides roughly twice per day. The Sun also influences tides, and when Sun and Moon align, their combined gravitational pull creates especially high spring tides. Earth's oceans play crucial roles in our planet's climate system. Water has a high heat capacity, meaning it can absorb large amounts of heat without changing temperature dramatically. The oceans store vast amounts of solar energy, releasing it slowly and helping stabilize Earth's temperature. Ocean currents transport this heat around the globe, making some regions warmer or cooler than they would otherwise be. The oceans also participate actively in Earth's carbon cycle. They absorb carbon dioxide from the atmosphere, with phytoplankton converting it into organic matter through photosynthesis. When these organisms die, some of this carbon sinks to the ocean floor, effectively removing it from the atmosphere for thousands or millions of years. The oceans have absorbed about 30% of the carbon dioxide humans have released since the Industrial Revolution, helping moderate atmospheric CO2 levels, but also causing ocean acidification. Life flourishes in Earth's oceans with extraordinary diversity, from microscopic bacteria to the largest animals ever to exist, blue whales reaching 30 meters in length. The oceans teem with organisms adapted to every conceivable niche. Photosynthetic phytoplankton drift in surface waters, producing about half the oxygen in Earth's atmosphere. Coral reefs, kelp forests, and seagrass meadows create complex ecosystems supporting thousands of species. Even in the deepest, darkest parts of the ocean, where no sunlight penetrates and pressures would crush a human instantly, specialized organisms thrive around hydrothermal vents, drawing energy from chemicals rather than sunlight. These hydrothermal vents, cracks in the ocean floor, where superheated water rich in minerals erupts from Earth's interior, represent particularly intriguing environments. Discovered only in 1977, these vents support ecosystems entirely independent of solar energy. Bacteria use the chemical energy in vent fluids to power their metabolism, and entire communities of organisms depend on these bacteria as their base energy source. The discovery of these chemosynthetic ecosystems revolutionized our understanding of where life can exist and how it can obtain energy. Earth's oceans have existed for billions of years, possibly forming within a few 100 million years of the planet's formation, about 4.5 billion years ago. The origin of Earth's water remains a subject of scientific investigation. Some likely came from asteroids and comets that bombarded the early Earth, while some may have been released from the planet's interior through volcanic activity. Over geological time, the volume and distribution of Earth's oceans has changed. During ice ages, when vast ice sheets covered much of the continents, sea levels dropped by more than 100 meters as water was locked up in ice. During warmer periods, sea levels rose. The oceans have also changed in chemistry, temperature, and the life they contain, responding to and influencing Earth's evolving climate and geological activity. Today, Earth's oceans face unprecedented changes due to human activities. Warming temperatures, ocean acidification, plastic pollution, and overfishing represent major challenges to ocean health. Yet the fundamental processes, the circulation, the tides, the interaction with atmosphere and geology, continue as they have for billions of years. As we now turn our attention to oceans beyond Earth, we carry this understanding of our own liquid world. Earth's oceans provide a framework for understanding how liquids behave on planetary scales, how they interact with their environments, and how they might support life. But as we'll discover, the cosmic ocean story extends far beyond our blue planet's familiar seas. Nearly 630 million kilometers from Earth, orbiting Jupiter once every 3.5 days, lies one of the most tantalizing worlds in our solar system, Europa, a moon where a vast ocean of liquid water sloshes beneath a shell of ice, containing perhaps twice as much water as all of Earth's oceans combined. Europa is the fourth largest of Jupiter's 95 known moons, with a diameter of about 3,100 kilometers, slightly smaller than Earth's moon. At first glance through a telescope, Europa appears as a bright, smooth orb, its surface whiter than any other large moon in the solar system. But closer inspection reveals a world of extraordinary complexity and beauty. When the Voyager spacecraft first flew past Europa in 1979, they returned images of a surface crisscrossed with dark lines and cracks, looking like a cracked eggshell or perhaps like the broken ice on a polar sea. Very few impact craters marked Europa's surface, a strong hint that the surface is geologically young, perhaps only 40 to 90 million years old. On a moon that has existed for over 4 billion years, this suggests active resurfacing processes. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, revolutionized our understanding of Europa. Its detailed images revealed that Europa's surface consists primarily of water ice, fractured into plates that have shifted and rotated over time. Dark reddish-brown lines streak across the surface cracks filled with material from below, stained perhaps by salts or sulfur compounds from Jupiter's radiation-soaked environment. But Galileo's most profound discovery came from its magnetometer, an instrument measuring magnetic fields. As Europa orbited through Jupiter's powerful magnetic field, Galileo detected a secondary magnetic field around Europa that changed in a specific, revealing way. This signature matched what scientists would expect from a layer of conducting fluid, likely a saltwater ocean beneath Europa's surface. Multiple lines of evidence now support the existence of this subsurface ocean. Europa's surface shows signs of chaos terrain, regions where the ice has broken into jumbled blocks that have rafted to new positions, like icebergs frozen in place. This behavior suggests that the ice shell floats atop liquid or semi-liquid material. Spectroscopic observations have detected what appear to be salts and possibly organic compounds on Europa's surface, consistent with ocean material reaching the surface. Models of Europa's interior suggest the following structure: a metallic iron core about 1,200 kilometers in diameter, surrounded by a rocky mantle. Above this lies the ocean, perhaps 100 kilometers deep, though estimates range from 80 to 170 kilometers. The ocean is covered by an ice shell, probably 15 to 25 kilometers thick, though again, estimates vary. In total, Europa may contain 3 billion cubic kilometers of water, more than twice the volume of all Earth's oceans. What keeps this ocean liquid, so far from the sun, where temperatures hover around -160 degrees Celsius at the surface? The answer is tidal heating. Europa orbits Jupiter in a slightly elliptical path, and Jupiter's immense gravity flexes Europa as the Moon's distance from the planet varies. Additionally, Europa is locked in orbital resonance with two other Galilean moons, Io and Ganymede. These gravitational interactions constantly squeeze and stretch Europa's interior, generating friction and heat enough to maintain a liquid ocean despite the frigid environment. The chemistry of Europa's ocean remains uncertain but intriguing. It likely contains dissolved salts, possibly similar to Earth's oceans but potentially quite different in concentration and composition. Magnesium sulfate, Epsom salt, may be abundant. The ocean may be slightly acidic or alkaline. Chemical exchanges between the ocean and the rocky mantle below could provide minerals and possibly chemical energy sources. Europa's ocean doesn't exist in isolation. The ice shell above constantly interacts with the liquid below. In some regions, warm ice may rise through a process called convection, while cold, dense ice sinks, creating a slow, churning circulation in the ice layer. Cracks and fissures may allow ocean water to reach the surface, where it freezes, potentially leaving chemical signatures of the ocean composition for us to detect. The bottom of Europa's ocean may harbor hydrothermal vents similar to those in Earth's oceans. As Europa's rocky mantle flexes and cracks due to tidal heating, seawater could circulate through cracks in the rock, becoming heated and enriched with minerals before emerging back into the ocean. Such vents could provide chemical energy sources for potential life. The possibility of life in Europa's ocean has captivated scientists and the public alike. The ocean appears to have existed for billions of years, plenty of time for life to emerge if the right chemistry occurred. The ocean contains liquid water, essential for life as we know it. Chemical energy may be available from interactions between water and rock. Organic compounds may be delivered by impacting comets, or may form through chemical processes within Europa itself. However, Europa's ocean also faces challenges as a habitat. It exists in total darkness. No sunlight penetrates through tens of kilometers of ice to power photosynthesis. Any life would need to derive energy from chemical sources, as organisms do at Earth's deep-sea vents. The ocean may be quite cold, perhaps -3 degrees Celsius or even colder, with dissolved salts lowering the freezing point. Jupiter's intense radiation bathes Europa's surface, though the ice shell shields the ocean from this harmful radiation. Recent observations have added to Europa's intrigue. The Hubble Space Telescope detected what may be plumes of water vapor erupting from Europa's south polar region, geysers of ocean water sprayed into space through cracks in the ice. If confirmed, these plumes could allow spacecraft to sample Europa's ocean without having to drill through kilometers of ice. Europa represents our best chance in the near future to explore an alien ocean. NASA's Europa Clipper mission, scheduled to launch in 2024 and arrive at Jupiter in 2030, will conduct detailed reconnaissance of Europa, mapping its ice shell, characterizing its ocean, and searching for suitable landing sites. Future missions may actually land on Europa and perhaps even drill through the ice to directly sample the ocean, though such a mission remains technically challenging. As you contemplate Europa, imagine an ocean of liquid water larger than all of Earth's seas, flowing in darkness beneath a shell of ice, warmed by the flexing caused by a giant planet's gravity. Imagine tides raised not by a modest moon but by massive Jupiter filling half the sky. Imagine the possibilities still unproven but tantalizing that something lives in those dark waters, evolving in isolation for billions of years, a form of life utterly independent of our own. If Europa is the grand ocean world of the inner solar system, Enceladus is its smaller, more active cousin in the realm of Saturn. This tiny moon, barely 500 kilometers in diameter, small enough to fit inside the state of Arizona, harbors a global ocean beneath its icy surface and actively sprays that ocean into space through spectacular geysers, creating one of the most dynamic and potentially habitable environments in the solar system. Enceladus is one of Saturn's 146 known moons, orbiting the ringed planet once every 1.4 Earth days at a distance of about 238,000 kilometers. For decades after its discovery in 1789, Enceladus seemed unremarkable, just another small icy moon among Saturn's many satellites. Its high reflectivity suggested a surface of fresh ice, but few expected the revelations that would come when spacecraft finally visited. The Voyager missions in the early 1980 seconds provided our first close-up views, revealing that Enceladus had regions of different terrain, ages, some heavily cratered, some mysteriously smooth. But the real revolution came with NASA's Cassini mission, which orbited Saturn from 2004 to 2017 and made multiple close flybys of Enceladus. In 2005, Cassini detected something extraordinary: plumes of water vapor and ice particles erupting from Enceladus's south polar region. These geysers spray material hundreds of kilometers into space at speeds up to 400 meters per second. The discovery was stunning. Here was direct visible evidence of liquid water escaping from inside a moon far from the sun, where surface temperatures plunged to -200 degrees Celsius. Cassini's instruments analyzed the composition of these plumes during multiple passes through them. The results revealed an ocean's chemical signature. Water vapor dominates, but the plumes also contain salt, sodium chloride, silica dust, simple organic compounds including methane, carbon dioxide, ammonia, and molecular hydrogen. This chemical cocktail provided direct samples of Enceladus's subsurface ocean, delivered conveniently to space for analysis. The southern polar region of Enceladus, where the plumes originate, shows a landscape unlike anywhere else in the solar system. 4 massive fractures, nicknamed tiger stripes, cut across the south polar terrain. These fractures, each about 130 kilometers long and 2 kilometers wide, glow with infrared heat, indicating they're warmer than the surrounding terrain. The plumes erupt from these tiger stripes, particularly from specific locations along them. How does Enceladus maintain a liquid ocean? Like Europa, the answer is tidal heating, though the mechanism is somewhat different. Enceladus orbits Saturn in resonance with another moon, Dione. This orbital resonance makes Enceladus's orbit slightly elliptical rather than circular. As Enceladus approaches and recedes from Saturn in its elliptical orbit, Saturn's gravity flexes the moon, generating heat through friction, enough heat to maintain liquid water despite Enceladus's small size and distance from the Sunday. The structure of Enceladus's ocean has been determined through careful analysis of the moon's wobble as it orbits. A solid, completely frozen moon would rotate differently than one with a liquid layer that can slosh around. Cassini's observations of Enceladus's rotation revealed that it has a global ocean. Water completely surrounds the rocky core. This ocean is estimated to be about 10 kilometers deep, lying beneath an ice shell that averages about 20 to 25 kilometers thick over most of the moon, but thins to perhaps 5 kilometers or less at the South Pole. The total volume of water in Enceladus's ocean is much smaller than Europa's, perhaps only as much water as Lake Superior, one of Earth's Great Lakes. Yet this relatively small ocean is remarkably accessible and well characterized thanks to the plumes, which provide free samples. The chemistry detected in the plumes has profound implications for habitability. The presence of salt indicates the ocean is in contact with Enceladus's rocky core, allowing water-rock reactions. The silica particles suggest hydrothermal activity, hot water interacting with rock, similar to Earth's deep-sea vents. Perhaps most intriguingly, the molecular hydrogen detected in the plumes likely comes from serpentinization, a chemical reaction between water and certain rock types that produces hydrogen gas and heat. This same reaction supports microbial life at Earth's hydrothermal vents. The simple organic compounds detected in the plumes, including methane and complex carbon-bearing molecules, demonstrate that the ocean contains the building blocks of life. Whether these organics formed through biological processes or non-biological chemistry remains unknown. But their presence in an environment with liquid water and chemical energy sources makes Enceladus one of the most promising places to search for life beyond Earth. The plumes themselves add to Enceladus's uniqueness. These eruptions aren't constant volcanoes, but rather geysers that pulse on and off, possibly influenced by tidal stresses that open and close the tiger stripes as Enceladus's distance from Saturn changes during its orbit. When open, ocean water rushes up through the fractures, flashing to vapor and ice as it hits the vacuum of space. Material from the plumes doesn't all fall back to Enceladus. Some escapes the Moon's weak gravity entirely, feeding Saturn's E-ring, a faint, gossamer ring of ice particles that extends from the orbit of Mimas to beyond the orbit of Titan. Enceladus essentially creates this ring, constantly replenishing it with fresh ice from its ocean. Every time you see an image of Saturn's rings, you're seeing, in part, frozen ocean water from Enceladus. The discovery of Enceladus's ocean and plumes has made this tiny moon a top priority for future exploration. Scientists have proposed missions to orbit Enceladus, to fly multiple times through the plumes collecting samples, and even to land near the South Pole. The plumes make Enceladus unique. We can potentially sample an alien ocean without having to drill through ice, simply by flying through the spray and analyzing what we collect. As you contemplate Enceladus, imagine a small, icy world orbiting a giant ringed planet, hiding a global ocean of salty water beneath its frozen surface. Imagine that ocean erupting through cracks in the ice, spraying into space in towering geysers, feeding a ring around the planet. Imagine hydrothermal vents on the ocean floor, warm water circulating through rock, chemistry happening in the darkness, and perhaps, just perhaps, simple life forms drawing energy from the chemicals. Evolving in this small ocean so far from the Sunday, our journey through liquid worlds now takes us to Saturn's largest moon, Titan, a world where liquid flows in abundance, but not water. On Titan's surface, beneath a thick, hazy atmosphere, lie seas and lakes of liquid methane and ethane, the only stable bodies of surface liquid known in the solar system beyond Earth. Titan is enormous as moons go larger than the planet Mercury, with a diameter of 5,150 kilometers. It's the second largest moon in the solar system, smaller only than Jupiter's Ganymede. But Titan's true uniqueness lies in its thick atmosphere, the only substantial atmosphere possessed by any moon. This atmosphere, discovered in 1944, is denser than Earth's, about 1.5 times the sea level pressure on our planet. It consists primarily of nitrogen, about 95%, with methane making up most of the remainder. Organic haze layers created by ultraviolet light breaking apart methane molecules, shroud Titan in an opaque orange veil, completely hiding the surface from view at visible wavelengths. For decades, scientists could only speculate about what lay beneath those haze layers. Some suggested Titan might have oceans of liquid methane or ethane covering its surface. When the Cassini spacecraft arrived at Saturn in 2004, carrying the European Huygens probe designed to land on Titan, humanity would finally see beneath the haze. Huygens descended through Titan's atmosphere on the 14th of January 2005, taking images and measurements during its 2.5-hour fall. The probe revealed a surface that was both alien and strangely familiar. No global ocean existed, but the landscape showed clear evidence of liquid erosion. Drainage channels carved by flowing liquid ran down hills. Rounded cobbles littered the landing site, smoothed by the tumbling action of flowing liquid. Titan appeared to be a world where liquid falls as rain, carves rivers, and collects in seas, a hydrological cycle much like Earth's, but with methane instead of water. Cassini's radar instrument, which could peer through the haze to map Titan's surface, revealed the full extent of Titan's liquid legacy. The Moon's northern polar region contains numerous lakes and 3 major seas. The largest, Kraken Mare, covers about 400,000 square kilometers, larger than the Caspian Sea on Earth, and holding perhaps 40 times the volume of North America's Great Lakes combined. Ligeia Mare, the second largest sea, is about the size of Lake Michigan and Lake Huron combined. Punga Mare is smaller but still substantial. These seas aren't water at Titan's surface temperature of -179 degrees Celsius. Water is frozen harder than rock. Instead, spectroscopic analysis confirms that Titan's seas consist primarily of liquid methane, CH4, and ethane, C2H6, with dissolved nitrogen and other hydrocarbons. These substances, which exist as gases on Earth, are liquids at Titan's frigid temperatures and moderate atmospheric pressure. Titan's liquid cycle mirrors Earth's water cycle in remarkable ways. Methane evaporates from the seas into the atmosphere, where it forms clouds. These clouds produce rain, methane rain that falls to the surface, runs off in rivers, and flows back to the seas. Cassini observed methane rainstorms, seasonal changes in cloud patterns, and even what appears to be monsoon season in Titan's tropics. The southern hemisphere shows fewer permanent lakes, but it does have one intriguing feature: Ontario Lacus, a lake about the size of Lake Ontario on Earth. This lake appears to fill and empty with the seasons. Titan has a year of about 29.5 Earth years as it orbits Saturn, and seasonal changes affect where liquid accumulates. Between the major seas lie numerous smaller lakes, particularly in the northern polar region. Some of these lakes sit in depressions with raised rims, features that suggest impact craters or perhaps collapsed karst formations, similar to limestone sinkholes on Earth, but formed by dissolution of organic material rather than carbonate rock. Some smaller lakes appear to be seasonal, filling during certain times of Titan's year and drying out during others. The depth of Titan's seas remains somewhat uncertain, as radar reflections from the sea floors are weak. Ligeia Mare appears to be at least 160 meters deep in places, possibly much deeper. Kraken Mare is likely even deeper. These depths, while substantial, are much less than Earth's ocean depths. Titan's seas are more like Earth's Great Lakes than Earth's oceans in scale. The composition of the seas varies somewhat between different bodies. Some lakes appear to be almost pure methane, while others contain more ethane, likely the result of methane breaking down into ethane over time as ultraviolet light from the sun breaks apart methane molecules in the atmosphere. The ethane then rains down and accumulates in the lakes. Some models suggest that after billions of years, Titan's seas might be primarily ethane rather than methane. Beneath Titan's icy crust lies another ocean, this one of liquid water. Like Europa and Enceladus, Titan appears to harbor a subsurface water ocean, perhaps 100 kilometers below the surface. Evidence for this ocean comes from the way Titan responds to Saturn's gravity, which causes tides not just in the atmosphere and surface liquid, but in the Moon's interior. The pattern of these tides suggests a layer of liquid between Titan's icy shell and its rocky core. This water ocean, if it exists as scientists believe, would be quite different from the surface methane seas. It likely contains ammonia or other antifreeze compounds to remain liquid at the temperatures expected in Titan's interior. It may be tens to hundreds of kilometers deep. Unlike the surface seas, which we can observe and study relatively easily, this subsurface ocean remains hidden and mysterious. The interaction between Titan's surface and subsurface environments creates intriguing possibilities. Impact craters might punch through to the water ocean below, creating temporary connections. Cryovolcanoes, ice volcanoes, might bring water or water-ammonia mixtures to the surface. The possibility of organic molecules from the surface reaching the water ocean, or vice versa, raises questions about exotic chemistry and perhaps even biology. Could life exist in Titan's methane seas? This question pushes the boundaries of our understanding of biology. Life, as we know it, requires liquid water, but some scientists speculate about alternative biochemistries using liquid methane as a solvent instead. Such life would be radically different from Earth life. Its molecules, its metabolism, its entire chemistry would be based on different principles. Whether such life could actually exist, or whether it does exist in Titan's seas, remains purely speculative. Future missions to Titan could explore these liquid environments directly. Concepts exist for boats or submarines to sail on Titan's seas, for landers to study the lake shores, for aerial vehicles to fly through the atmosphere and sample rain as it falls. NASA's Dragonfly mission, scheduled to launch in 2027 and arrive at Titan in 2034, will be a rotorcraft, a large drone that will fly between different locations on Titan, studying its chemistry and searching for signs of habitability. As you contemplate Titan, imagine standing on a shore not of water but of liquid methane, looking out over a sea that would freeze solid if moved to Earth. Imagine methane rain falling from orange skies, carving rivers through water ice as hard as rock. Imagine seasonal cycles playing out over decades as this distant world orbits its ringed giant planet. Imagine a subsurface ocean of water deep below, and wonder what strange chemistry might occur where Titan's exotic surface meets its hidden water ocean. Europa, Enceladus, and Titan represent the most famous liquid worlds beyond Earth, but they're not alone. Several other moons in the outer solar system likely harbor subsurface oceans, each adding to our understanding of how and where liquid water can exist. Ganymede, Jupiter's largest moon and the largest moon in the solar system, shows evidence for a subsurface ocean possibly larger than all of Earth's oceans combined. With a diameter of 5,268 kilometers, Ganymede is larger than the planet Mercury. Its surface consists of two main terrains: dark, heavily cratered regions, representing ancient surface, and lighter, grooved terrain, showing evidence of more recent geological activity. The Galileo spacecraft's magnetic field measurements suggested that Ganymede has its own magnetic field, the only moon in the solar system with such a field generated by a molten iron core. But more intriguingly, the measurements also showed a secondary magnetic signature consistent with a layer of conducting fluid, likely a salty ocean, beneath the surface. Ganymede's ocean probably lies deeper than Europa's, perhaps 150 to 200 kilometers below the surface, beneath multiple layers of ice of different crystal structures. The immense pressure at this depth would create exotic forms of ice, denser than normal ice, possibly creating a sandwich structure, with the ocean trapped between layers of ice above and below. The total volume of water could exceed 25 times all water on Earth's surface. This deep ocean likely remains liquid due to a combination of residual heat from Ganymede's formation and possible tidal heating, though Ganymede's tidal heating is much less than Europa's. The ocean floor might be in contact with Ganymede's rocky mantle, potentially allowing the water-rock interactions that could provide chemical energy for life. However, the great depth and possible isolation of the ocean make it less accessible and perhaps less hospitable than Europa's ocean. Callisto, the second largest Galilean moon of Jupiter, may also harbor a subsurface ocean. Slightly smaller than Mercury, Callisto has the most heavily cratered surface in the solar system, ancient terrain showing little evidence of geological activity. Yet magnetic field measurements by Galileo suggested a conducting layer consistent with a subsurface ocean. If an ocean exists within Callisto, it likely lies very deep, perhaps 200 kilometers or more below the surface. With little tidal heating and an old inactive surface, Callisto's ocean, if it exists, might be one of the least dynamic ocean environments we know. Yet even such a quiescent ocean, stable for billions of years, raises questions about habitability. Mimas, a small moon of Saturn, recently surprised scientists with possible evidence of a subsurface ocean. Mimas looks like the Death Star from Star Wars, thanks to a giant impact crater named Herschel that dominates one side. For decades, scientists assumed Mimas was simply a frozen, inactive ball of ice. But careful analysis of Mimas's rotation revealed a wobble consistent with either an elongated core or a global subsurface ocean. If Mimas has an ocean, it's remarkable because the surface shows no signs of the geological activity that usually indicates an ocean below. Perhaps the ocean is very recent, or perhaps Mimas's ice shell is thick and rigid enough to prevent surface features from forming. The possible ocean would be relatively small, and its very existence remains uncertain, but it demonstrates that we may not yet understand all the ways oceans can hide beneath icy surfaces. Dione, another moon of Saturn, shows signs of past geological activity, fractures and smooth plains, suggesting internal heat and possibly liquid water in the past. Some scientists suspect it might still harbor a subsurface ocean, though evidence is less clear than for other moons. Dione's orbit and gravitational relationship with Enceladus might provide enough tidal heating to maintain an ocean, but this remains speculative. Triton, Neptune's largest moon, presents an intriguing case. Captured by Neptune's gravity long ago, Triton orbits backwards compared to Neptune's rotation, a unique characteristic among large moons. Voyager 2's flyby in 1989 revealed active nitrogen geysers erupting from Triton's surface, demonstrating internal activity. Some models suggest Triton could have a subsurface ocean of water mixed with ammonia, kept liquid by radioactive decay and possibly residual heat from tidal heating when Triton's orbit was more elliptical. Even Pluto, now classified as a dwarf planet in the Kuiper Belt, may harbor a subsurface ocean. Data from NASA's New Horizons flyby in 2015 suggested that Pluto's Sputnik Planitia, a vast plain of nitrogen ice, might be positioned where it is due to a subsurface ocean creating a mass concentration. A layer of liquid water, perhaps 100 kilometers thick, might exist beneath Pluto's icy surface, kept liquid by radioactive decay in the rocky core and the insulating effect of a layer of gas hydrates. These potential ocean worlds span the solar system from Jupiter to the Kuiper Belt, from large moons to dwarf planets. Each ocean environment differs in depth, composition, temperature, and accessibility. Some oceans might be in direct contact with rocky cores, allowing the water-rock chemistry that could support life. Others might be isolated between layers of exotic ice, cut off from chemical energy sources. The diversity of possible ocean worlds suggests that liquid water may be common in the outer solar system. Where previous generations of scientists thought the outer solar system was a frozen wasteland, we now see a realm of hidden oceans, each potentially harboring conditions suitable for life. The ice shells that seem to rule out habitability actually insulate and protect these oceans, allowing them to persist for billions of years. As you contemplate these many ocean moons, imagine a solar system far richer in liquid water than we ever imagined, not on surfaces exposed to space, but hidden safely beneath protective shells of ice, warmed by the interior heat of worlds that seemed frozen and dead. Imagine that beneath the icy cruises of dozens of moons, water flows in darkness, perhaps simple life forms swimming in those hidden seas, entire ecosystems evolving in isolation, unknown to us. Our journey through liquid worlds now takes us beyond our solar system to planets orbiting other stars. Among the thousands of exoplanets discovered since the 1990 seconds, scientists have identified a category of particular interest: ocean worlds, planets where water might cover the entire surface without any land. Water worlds, hypothetical planets consisting primarily of water, could form in several ways. They might begin as icy planets formed in the cold outer regions of planetary systems, then migrate inward closer to their stars. As they warm, the ice melts, creating global oceans potentially hundreds of kilometers deep. Alternatively, they might form from material rich in water ice, accreting enough water that it becomes a major component of the planet's structure. The structure of an ocean world differs dramatically from Earth. On our planet, water represents only about 0.02% of total mass, forming a relatively thin layer over the rocky surface. On a true water world, water might constitute 10% or even 50% of the planet's mass. Such planets would have structures consisting of a rocky or metallic core, surrounded by a massive water layer, potentially topped by a thick atmosphere. Under the immense pressure of hundreds of kilometers of overlying water, bizarre forms of ice would exist even at high temperatures. Ice 7 and Ice X, forms of ice that remain solid at temperatures where normal ice would melt, could form a layer between the liquid ocean and the rocky core. These exotic ices are crystalline forms denser than liquid water, created by extreme pressure, squeezing water molecules into compact arrangements impossible at normal pressures. Imagine descending into such an ocean world. The surface might be a relatively normal ocean, with liquid water exposed to a thick, steamy atmosphere. But diving deeper, you'd pass through a layer of normal liquid water, perhaps 100 kilometers thick. Below this, pressure would become so intense that you'd reach a layer where water remains liquid but becomes so compressed that its properties change, perhaps becoming a superionic state where hydrogen ions flow through a lattice of oxygen atoms like electrons through a metal. Deeper still, at pressures millions of times Earth's sea level pressure, you'd encounter the exotic ice layers solid, despite temperatures of hundreds or even thousands of degrees Celsius. Only at the very center would you finally reach the rocky core, a world unto itself, squeezed and heated by the weight of all that water above. Could life exist on such worlds? This question challenges our assumptions about habitability. Earth's oceans teem with life, but they exist in contact with a rocky surface where minerals and nutrients are accessible, where hydrothermal vents provide chemical energy, where light penetrates the upper layers powering photosynthesis. A true ocean world might lack many of these features. A global ocean hundreds of kilometers deep might be cut off from its rocky core by layers of exotic ice, preventing the water rock chemistry that provides nutrients and chemical energy on Earth. Without land to create shallow seas and tidal zones, without breaking waves and coastal ecosystems, an ocean world's biology, if any, might be very different from Earth's. Photosynthesis could only occur in the very surface layers if the atmosphere allowed sunlight through, and even then, nutrients might be scarce. However, some models suggest that ocean worlds might be more habitable than initially thought. If the exotic ice layer is permeable, or if it has cracks due to geological activity, water could circulate down to contact the rock and return enriched with minerals. Tidal heating from gravitational interactions with other planets or moons could generate heat and possibly volcanism. Ocean currents could distribute nutrients. Life might find ways to thrive in these global oceans, perhaps very different from Earth's life but viable nonetheless. Several exoplanets have been proposed as possible water worlds based on their mass and density. Planets like GJ 1214b, a super-Earth orbiting a red dwarf star about 48 light-years away, have densities consistent with substantial water content. K2O-18b, another super-Earth about 124 light-years away, has atmospheric observations suggesting water vapor, raising speculation about a water-rich world. The recently discovered TRAPPIST-1 system, with 7 Earth-sized planets orbiting an ultra-cool dwarf star about 40 light-years away, includes several planets that might be water worlds. Estimates suggest some TRAPPIST-1 planets could have water masses up to 15% of their total mass, far more than Earth. If correct, these planets might have global oceans tens or hundreds of kilometers deep. Determining whether an exoplanet is truly a water world remains challenging. We can measure a planet's mass from its gravitational effect on its star, and its size from the amount of starlight it blocks when it passes in front of its star. From mass and size, we calculate density. A density between that of rock and that of hydrogen, helium gas, suggests substantial water content. But this method isn't definitive. A planet could have a large atmosphere of light gases instead of water, or it could have a different composition altogether. Future telescopes and techniques promise better characterization of exoplanet compositions. The James Webb Space Telescope can analyze the atmospheres of some exoplanets, searching for water vapor and other molecules. Future missions designed specifically to study exoplanets might be able to detect reflections from global oceans or measure atmospheric properties that reveal water-rich worlds. Some scientists have proposed searching for ocean worlds by looking for specific atmospheric signatures. A water world with a warm surface might have a steamy atmosphere rich in water vapor. The spectrum of light passing through such an atmosphere during a transit, when the planet passes in front of its star from our viewpoint, would show strong water absorption features. Distinguishing a water world from a planet with water vapor in its atmosphere, but no surface ocean, remains a challenge, but multiple observations across different wavelengths could potentially make the distinction. The diversity of possible ocean worlds is enormous. Some might be warm water worlds orbiting close to dim red dwarf stars, with surface temperatures comfortable for liquid water, but with perpetual daylight on one side and eternal night on the other. Others might be cold water worlds farther from their stars, with frozen surfaces covering deep liquid oceans, much like the moons of our outer solar system. Some ocean worlds might have substantial atmospheres, possibly creating greenhouse effects that keep the surface warm. Others might have minimal atmospheres. The presence and composition of atmospheres would dramatically affect these worlds' surface conditions, ocean chemistry, and potential for life. As you contemplate these distant ocean worlds, imagine planets where water flows in quantities that dwarf Earth's oceans, where the entire surface is sea without any land, where exotic forms of ice exist at the boundary between ocean and core. Imagine the possibility of life in these global oceans, swimming in warm seas under alien skies, or perhaps existing in the utter darkness of oceans cut off from their stars by thick ice crusts. Each of these worlds tells a different story of how water, the universal solvent, the molecule essential for life as we know it, can exist in myriad forms across the cosmos. The exploration of liquid worlds stands at an exciting threshold. Within the next few decades, missions to explore these watery worlds in detail will transform our understanding and might even discover life beyond Earth. Europa Clipper, NASA's flagship mission to Jupiter's moon, will launch in 2024 and spend 4 years traveling to the Jovian system, arriving around 2030. Rather than orbiting Europa directly, which would expose the spacecraft to intense radiation, Europa Clipper will orbit Jupiter while conducting nearly 50 close flybys of Europa, some as low as 25 kilometers above the surface. Europa Clipper's instruments will study Europa's ice shell, measuring its thickness and searching for the best locations for potential future landers. Cameras will image the surface in unprecedented detail. An ice-penetrating radar will probe the structure of the ice shell and potentially detect the ocean below. A magnetometer will characterize the ocean's depth and salinity. Instruments will analyze any material erupted from the surface, searching for organic compounds. If plumes are erupting, as Hubble observations suggest, Clipper might fly through them, sampling ocean water directly. Beyond Europa Clipper, concepts exist for even more ambitious missions. A Europa lander could touch down on the surface, drill or melt into the ice, and sample material from the ocean. Such a mission faces immense technical challenges: the intense radiation environment, the difficulty of landing on unknown terrain, the complexity of drilling through ice, but it's technically feasible with focused development. The ultimate mission to Europa would be a submarine or probe that melts through the ice shell and enters the ocean directly. This concept, called a cryobot, to melt through ice, and hydrobot, to explore the ocean, represents perhaps the most challenging robotic mission ever conceived. The probe would need to melt through 15 to 25 kilometers of ice, avoiding getting stuck, maintaining communication, and preserving enough power to operate once it reaches the ocean. Then it would need to explore the ocean, search for life, and communicate its findings back through kilometers of ice. Such a mission likely lies decades in the future, but it's not impossible. Enceladus also beckons for future exploration. The Enceladus Orbilander, a proposed mission, would orbit Enceladus while repeatedly flying through the plumes, collecting and analyzing samples. Eventually, it would land near the South Pole, studying the tiger stripes up close and perhaps sampling fresh plume material that has fallen back to the surface. Enceladus offers unique advantages for searching for life. The plumes bring ocean material to space, where it can be sampled without drilling. Any life in the ocean, if it exists, might be present in the plume particles. Advanced instruments could potentially detect chemical or even structural signatures of life. And if the plumes contain living microorganisms from the ocean, we might be able to collect them, study them, and confirm life beyond Earth. Titan will host NASA's Dragonfly mission, a rotorcraft lander that will arrive in 2034. Dragonfly will fly between different locations on Titan, studying its unique environment, where organic chemistry occurs in methane lakes, and possibly where organic molecules from the surface interact with liquid water from the subsurface ocean. While Dragonfly won't directly explore Titan's methane seas or water ocean, it will investigate the chemistry that makes Titan potentially habitable. Concepts for exploring Titan's seas directly include boats or submarines that could float on or dive into Kraken Mare or Ligeia Mare. Such vehicles could study the sea's composition, depth, and dynamics, search for exotic life based on methane biochemistry, and perhaps sample deposits on the sea floors. The technical challenges are different from ocean exploration on Earth. Methane's low density and Titan's low gravity create different buoyancy conditions, and the extreme cold affects materials and operations, but these challenges aren't insurmountable. For exoplanet ocean worlds, direct exploration lies far in the future, but remote observations will continue improving. The James Webb Space Telescope and future observatories will characterize exoplanet atmospheres in increasing detail. Next-generation telescopes, including space-based missions specifically designed to study exoplanets, might be able to detect oceans on nearby worlds through spectroscopy, polarization studies, or even crude imaging. The search for biosignatures, signs of life on ocean worlds, will employ multiple approaches. On Europa and Enceladus, instruments will analyze the chemistry of surface or plume materials, searching for organic molecules in patterns suggesting biology, looking for amino acids with the homochirality, handedness, characteristic of life, detecting chemical disequilibrium that might indicate metabolism. Future missions might search for more direct signs. Could we detect organisms in plume particles or surface ice? Could we image bacterial colonies or more complex life forms if they exist? Could we detect the byproducts of metabolism, the way oxygen in Earth's atmosphere reveals photosynthetic life? These questions drive the development of increasingly sophisticated instruments. The possibility of contaminating pristine ocean environments with Earth life presents profound ethical and scientific challenges. International planetary protection protocols require that missions to potentially habitable worlds be carefully sterilized to avoid forward contamination, bringing Earth microbes that could multiply and confound the search for native. For ocean access missions, even stricter protocols will be necessary, ensuring that any life we detect is genuinely native rather than contamination from Earth. New technologies will enable these missions. Autonomous systems will allow spacecraft and landers to make decisions without waiting for commands from Earth, essential when exploring dynamic environments like plume eruptions. Advanced power systems, including nuclear radioisotope generators, will provide the energy needed for long missions in the dark outer solar system. Miniaturized instruments will pack extraordinary analytical capability into small packages suitable for spacecraft with limited mass budgets. Machine learning and artificial intelligence will play increasing roles in analyzing data from ocean worlds. The sheer volume of information from high-resolution images, spectroscopy, and other instruments exceeds human capacity to examine manually. AI systems can identify interesting features, classify surface types, and even search for patterns that might indicate life. As these missions unfold over the coming decades, they will reshape our understanding of where and how life can exist. If we find life in Europa's ocean, Enceladus's plumes, or any other liquid environment beyond Earth, it will suggest that life arises readily wherever liquid, water, and energy coexist for extended periods. This would imply that the universe teems with life, that among the billions of stars and planets, inhabited worlds are common. Conversely, if we explore multiple ocean worlds and find them all lifeless despite having the conditions we think necessary for life, we'll need to reconsider our understanding of life's origin and requirements. Perhaps life is much rarer than we think. Perhaps additional factors beyond liquid water and chemical energy are essential. The absence of life would be, in its own way, as profound a discovery as its presence. As our journey through the liquid worlds of the cosmos comes to a gentle close, let us reflect on what these watery realms teach us about our universe and our place within it. Liquid water, that simple molecule of 2 hydrogen atoms and 1 oxygen atom, proves to be far more common in the universe than we once imagined. From the subsurface oceans of icy moons to possible global seas on distant exoplanets, water flows in abundance, creating environments where the chemistry of life might unfold. Earth, our blue marble, is not unique in its water wealth. Indeed, several moons in our own solar system contain more liquid water than all of Earth's oceans combined. Our planet may be exceptional in having liquid water at its surface, exposed to sunlight and atmosphere, readily accessible for life to utilize. But for sheer volume of water, Earth is modest compared to the ocean moons of the outer solar system. This realization transforms our perspective on habitability and the search for life. We once thought that life required Earth-like conditions, a rocky planet in the habitable zone of a sun-like star, with surface oceans and continents, with an oxygen atmosphere. We now understand that life might thrive in far more diverse environments, beneath the ice shells of moons, in global oceans, on water worlds, perhaps even in exotic liquids like Titan's methane seas. The liquid worlds we've explored show remarkable diversity. Europa's ocean churns beneath a dynamic ice shell, possibly harboring hydrothermal vents in its dark depths. Enceladus sprays its ocean into space through active geysers, providing free samples for our instruments to analyze. Titan's methane lakes and seas create an alien yet familiar landscape, with rain and rivers and seasonal changes, all in liquids that would freeze solid on Earth. Ganymede harbors a vast ocean trapped between layers of exotic ice, isolated yet enduring for billions of years. Each of these worlds tells a different story of how planets and moons can maintain liquid environments, tidal heating, radioactive decay, residual heat from formation, insulation by thick atmospheres or ice layers. Multiple mechanisms can keep liquids flowing even in the cold reaches of the outer solar system or in the dark depths beneath planetary crusts. The presence of these oceans raises profound questions about life in the universe. If life exists in these hidden seas, it evolved independently of Earth life, perhaps following different chemical pathways, creating different molecules, operating on different energy sources. Such life might be simple bacteria-like organisms in the water, or it might have evolved greater complexity over billions of years in stable ocean environments. Discovering life in these oceans would be one of humanity's greatest achievements, comparable to Copernicus revealing that Earth orbits the Sun, or Hubble showing that the universe extends far beyond our galaxy. It would confirm that life is not confined to Earth, that the universe has produced biology in multiple locations, that we are not alone in the cosmos. Even if we find these oceans lifeless, we will have learned something profound. We'll have better understood the conditions necessary for life, the challenges that prevent it from arising or persisting, the balance of factors required for biology to emerge from chemistry. And we'll have explored some of the most exotic environments in the solar system, pushing the boundaries of human knowledge and capability. There's also a poetic beauty to these liquid worlds, water in all its forms flowing as ocean currents, erupting through geysers, frozen in elaborate ice structures, existing as exotic phases under extreme pressure, demonstrates the richness and diversity of the physical universe. The same chemical compound arranges itself in dozens of ways, depending on temperature and pressure, creating environments of extraordinary variety. The methane seas of Titan remind us that liquid isn't limited to water. Chemistry can create flowing substances from many molecules. While life as we know it depends on water, we can't rule out the possibility of life based on other solvents operating on entirely different principles. The universe may be more creative than our imaginations. As you drift towards sleep, contemplate these liquid worlds scattered throughout the cosmos. Imagine Europa's ocean, larger than all Earth's seas, churning in darkness beneath a shell of ice, warmed by the gravitational pull of Jupiter. Imagine Enceladus's geysers spraying ocean water hundreds of kilometers into space, creating Saturn's E-ring from frozen droplets. Imagine Titan's methane rain falling from orange skies, filling seas that lap against shores of water ice harder than rock. Imagine distant exoplanets entirely covered by global oceans, water worlds where depths plunge hundreds of kilometers into bizarre ice phases. Imagine the possibility, still unproven, but tantalizing, that something lives in these alien seas, that simple organisms swim in Europa's ocean, that microbial life draws energy from chemicals at Enceladus's hydrothermal vents, that exotic biochemistry unfolds in Titan's methane lakes. These liquid worlds connect us to the cosmos in intimate ways. The water in Earth's oceans, the water in our bodies, shares a common origin with the water in Europa's ocean, in Enceladus's plumes, in the subsurface seas of distant moons. We are all part of the same cosmic story, the same chemical evolution that has distributed water and other molecules throughout the universe. The exploration of these worlds represents humanity at its best, curious, persistent, innovative, reaching beyond the familiar to understand the unknown. Each mission to an ocean world carries our questions, our instruments, our desire to know. What lies in those hidden depths? Are we alone? What wonders await discovery? The answers, when they come, will reshape our understanding of life, of habitability, of our place in the universe. They may confirm our hopes that life is common, or they may teach us that Earth is more special than we thought. Either answer will be profound, either will expand our knowledge and deepen our appreciation for the cosmos. As you rest, as sleep takes you, let your mind drift among these watery worlds. Dream of oceans beneath ice, of geysers erupting into space, of methane rain and water seas, and exotic chemistry unfolding in darkness. Dream of future explorers, both human and robotic, diving into these alien oceans, discovering what has been hidden for billions of years, perhaps touching life that evolved in isolation, perhaps finding only sterile water, but learning nonetheless. The liquid worlds await our exploration. They've existed for eons, their oceans flowing in darkness, their chemistry unfolding in silence, their secrets preserved beneath ice and distance. But now, for the first time in history, we have the capability to reach them, to study them, to potentially discover whether we share the universe with other forms of life. Rest well, cosmic explorer. Tomorrow the exploration continues, the questions persist, the search for understanding goes on. But tonight, let the gentle rhythm of distant oceans lull you to peace. The liquid worlds of the cosmos spin silently in their orbits, their seas waiting patiently for the day when human ingenuity reaches them at last. May your dreams be filled with watery wonders and cosmic mysteries, with oceans both familiar and strange, with the endless possibilities these liquid worlds represent.